Hello, my name is Natalie Williams, and this is my fourth lab on oscillations. So here's the introduction to the lab. The purpose of the lab was to analyze the motion of a mass oscillating on a spring system in an arcing motion similar to a pendulum, and we used the tracker app to gather information about the object's position vector over time. And then we built a computational model of the motion to analyze the changing energy. And the system itself was the mass and the spring. Here we have some fundamental principles used throughout the lab. First, we have the energy principle, which involves gravitational potential energy, kinetic energy, and spring potential energy in this particular lab. Please pause the video to see any formulas that we use throughout the code and throughout the lab. In terms of our position vectors, the force of gravity, or the force vectors, the force of gravity is downwards in terms of the unit vector, and the force from the spring is positive, just to note that down. So the fundamental principles part 2. To satisfy the energy principle in order to predict the motion, we need to account for the net force acting on our object, which will allow us to find the changes in energy. So here we have the weight force and the spring force, and then we use Newton's second law to calculate the spring constant and the relaxed length, as seen here. And we get that the relaxed length is 0.123 meters, and the spring constant is 6.83 Newton meters. For the tracker analysis, as you can see from the preview on the right of this image, this has an oscillatory pattern which shows that there's an amplitude and a time period. So here's my code. For the initial part of the code, we just set up the initial conditions, so the mass of the object and initial position vectors using tracker. We set up the length vector using the unit vector and S, which is the change of position. And then we compute the various energies in the system using the energy principle, particularly, as I'll say later, the initial energies. And part 2 of the code, we calculate the different forces enacting on the system and the net force. And then here we calculate the change in the potential energies and kinetic energy. It's important to note here that work is just a change in energy, and the value of work is the force vector times the change in position, and thus that's why we use these forces. Oh, excuse me. Here we have my energy graph. This is highly important. So red is the change in gravitational potential energy, green is the change in the spring potential energy, and these oscillate within the same period because as the gravitational potential energy increases, the spring potential decreases because they're in opposition. And then blue is the change in kinetic energy. So the object gains and loses kinetic energy, but it loses it twice as fast as the potential energy. And the kinetic energy is greatest when the potentials are 0, which is middle of the swing. Orange is the change in total energy, and as it can be seen, this is constant. As the entire system is the mass and the spring, so the potential and the kinetic energies are always equivalent in magnitude. Here's my graph comparison of the x position versus time and y position versus time. It's important to note that that drag and human error and minuscule losses of energy are not accounted for in the predicted model. As you can see, the spring stayed relatively straight due to the unit vector, and the y position kind of faltered as a result of human error as well. So now we're on to the analysis. What does it mean? Is the energy principle satisfied? So gravitational potential energy and spring potential energy oscillate within the same period, but they have opposite phases. As you can see, what a phase is on the right, while kinetic energy is increasing and decreasing mostly in opposition to the potentials, but due to some error, it kind of is all over the place. This makes the total energy change 0 because the system is isolated, meaning that the system isn't really having much interaction with the surroundings. However, human error made slight discrepancy in the graph of the tracker system. So yes, the energy principle is apparent in the graph, but there are some mistakes. And then finally, we compare the period of oscillation for both the x and y position data. So the period in the x direction that I calculated was 1.633 seconds, and the period in the y direction was 1.501 seconds. And these are not the same, but this is most likely due to the fact that the period in the y direction is vertical motion, like a spring. Well, it is a spring, but x is related to simple harmonic motion of a pendulum, so these have different motion characteristics, which make the periods different. And that is all. Thank you.